Hi everyone, welcome to the first lecture. First is just a reminder that in this class we will use what's called International System of Units. It's based on three basic or fundamental units. Those are lengths, square brackets, mean that I'm talking about units. The unit is 1 meter, originally defined as 1/10 millionth of a distance from North Pole to equator. Nowadays, the unit of length is defined through the speed of light, distance light will travel during such and such time. Subunits: 1 centimeter is 10 to negative 2 meters. 1 millimeter is 10 to negative 3 meters. 1 micrometer, Greek letter mu, 10 to negative 6 meters. 1 nanometer is 10 to negative 9 meters. 1 nanometer scale is an atomic scale. Okay, up 1 kilometer is 10 to the third meters. Second basic unit is unit of mass. In SI system, this is 1 kilogram. Going down, 1 gram is 10 to negative 3 kilograms. 1 milligram is 10 to negative 6 kilograms. 1 microgram is 10 to negative 9 kilograms. Going up, 1 ton is 10 to the third kilograms. 1 kilogram was originally defined as mass of 1 liter or 1 cubic decimeter of distilled water. And time one second. 1 millisecond is 10 to negative 3 seconds. 1 microsecond is 10 to negative 6 seconds, and 1 nanosecond is 10 to negative 9 seconds, and so on and so forth. 1 minute is 60 seconds. 1 hour is 60 minutes, or 3,600 seconds. Those are basic units of International System of Units. And in most of the cases, you will have to convert to standard units. So if you have distance given in kilometers, you must convert it to meters. If mass is given in tons, you must convert it to kilograms. If time is given in microseconds, you must convert it into seconds. How to do the conversion. The conversion is done using so-called chain link conversion. So, for example, 362 tons needs to be converted into kilograms. So we will always use, for example, 1 ton over 1000 kilograms is nothing but 1. So, or we can rewrite it as 1000 kilograms over 1 ton. So what I need to get rid of tons and replace it with kilograms. So here we go, 362 tons divided times 1000 kilograms divided by 1 ton, which makes 362,000 kilograms, or 3.62 times 1, 2, 3, 4, 5, 10 to the 5 kilograms. Every other unit in this class will be some combination of those 3 standard units. And in the next 11C class, we'll also introduce 2 new units, charge one new unit charge, which I will show you how to deal with. Okay, so the next step is we will review the concept of vectors. Vectors are actually mathematical objects. Nevertheless, physics uses the concept of vector very extensively. So, what is the vector? Vector is a class of object which is characterized by 2 parameters. First one is the magnitude of a vector, or a number we assign to vector quantity, and second one is a direction. Guys, vectors are not numbers. There are particular rules how to operate with vectors, and you cannot just add magnitudes as numbers. So, in 2D space on xy plane, vector is shown as an arrow. The number we associate with a vector, which we will call the magnitude of the vector, and the direction. So the length of this arrow is actually proportional to the magnitude of the vector, and the angle vector makes with positive x-axis, let's call it theta, and vector normally shown as a letter with little arrow. This angle theta determines the unique direction of vector in space. Guys, as you can see, the concept of vector without a system of coordinates has absolutely no meaning. The direction is always associated with some predetermined direction in space. There are two different ways to deal with a vector. First one is graphical. So that's exactly what I did in this picture. We show the angle and we show an arrow with lengths proportional to the magnitude of a vector. Second one is using trig, or in math we say using vector components. So if I will imagine that I need to get from point O to point A, I can get from O to A using any arbitrary path in space. The simplest one, of course, is to go directly from O to A. And, for example, if we're talking about the displacement, then the number of steps along the line, which is tilted by the angle theta with respect to positive x-axis. Now, we can actually replace this path with conceptually simpler one. So, if I'm talking about the displacement in space, I can walk from point O to this point and from this point to point A. Note, I'm walking along two principal axes always. Now, if I will take a look at this whole figure, that is nothing but a right angle triangle. And we know how to deal with right angle triangles using trig. So, again, I can replace vector A with two equivalent displacements. Vector A, and I will call it A of x along a x-axis, and vector A of y along y-axis. As you can see, that the final result is identical if I will walk from point O to point A, or I will walk from along A of x and then along A of y. Now, if the final result is absolutely identical, then I can define the operation of vector addition, or how to add two vectors. So immediately I will write that vector A is nothing but vector A of x plus A of y. If you will take a look again, vector A of x and vector A of I are or A of y are arranged what we call head to tail. So now, expanding what I already said, if I have two vectors, vector A again and vector B. To add two vectors graphically, all I need is to arrange vector A and B head to tail. Now you will say, how? Very simple. The cardinal rule about vectors is as follows. Two vectors represent the same vector if they have the same magnitude and the same direction. Guys, please listen very carefully. One more time. I did not say two vectors are equal to each other. It's bigger than that. Two vectors represent the same vector. It's identical vectors if they have the same magnitude and the same direction. So if I will take a look here, here is my vector B. If I will actually move it to the tip of vector A, this is still my vector B. And exactly as here, the resultant vector A plus B will connect the beginning of vector A and the end of vector B. So here we go. Vector C is nothing but A plus B. This is graphical method of adding two vectors. Now, what if I need B plus A? Then I will do exactly same. I will move vector A to the tip of vector B, and as you can see from this sketch, it's also vector C, and B plus A is the same as A plus B. Therefore, vector addition conforms to what we call commutative law. Now, of course, I can use a ruler, I can use proportions, I can calculate the magnitude of vector C, or measure the magnitude of vector C, and I can measure using protractor the angle vector C makes with positive x-axis, but the result will be not precise. As you will learn in your lab, any measurement is associated with some sort of uncertainty. We will actually use trig to actually find the resultant vector C, and to find the resultant vector C means two things. We need to find the magnitude of vector C and the angle vector C makes with positive x-axis. Okay, can I measure the angle with respect to any other axis? Of course I can. That will still give me a unique direction in space, but the common way to represent the direction of the vector is counterclockwise with respect to positive x-axis. So, for example, for a vector B, The angle vector B makes with positive x-axis is this one. Okay, so one more time. A of x and A of y are two vectors which, according to vector addition, can replace vector A. Those are called vector components. Next, we will introduce what's called scalar components. Note, A of x and A of y are along principal axis, which means that the number of steps is the only parameter I need to know. Number of steps in x direction and number of steps in y direction. However, I can also sketch, let's sketch my vector B here. So here is my B of x vector and B of y vector. However, for a vector B, I need to walk in negative direction of x-axis. And if I will sketch a vector in the third quadrant, I need to walk both negatives along x and y directions. So as you can see, when we're talking about A of x vector component and A of y vector component, I can simply replace A of x vector with its magnitude and indicate plus or minus depending on the orientation of A of x or B of x. So now the next operation with vectors, which we will introduce right here, which will actually allow us to introduce scalar components, is operation of multiplication of a vector by a number. So let's say, for the sake of simplicity, I will write vector A times 1. The operation of multiplication of a number by a vector is very simple. To find the resultant vector, and the result of this operation is a vector. To find the resultant vector, we need to multiply the magnitude of vector A by absolute value of a number and the direction of the resultant vector will be preserved if number is positive and the direction of the resultant vector will be changed to opposite if number is negative. So take a look. A times 1, magnitude multiplied by 1 will be the same, will stay the same, and the direction will stay the same. So, for example, A times 1 gives me exactly A. A times -1 gives me a vector of the same magnitude as A, but opposite in direction, -A. So if I want to, for example, here is my vector A. For example, 2 times A. Let's call it B. So what do I need to do? I need to multiply magnitude of vector A by 2. So it's going to be 2 times greater. And the direction of vector B will be the same as the direction of vector A. So here we go. This is my vector B. Now, if I want vector C, which is -2 times A, so vector C will have twice the magnitude of vector A, but the direction of vector C will be opposite to the direction of vector A. So here we go. I will try to do my best. Vector C, which is -2 times A. So, next, on xy plane, I will define two unit vectors. In xyz system of coordinates, I will define 3 unit vectors. So those 2 unit vectors will be in positive direction of x and positive direction of y. I will call them I and j. Those names are given to unit vectors in the direction of positive principal axis by convention. So I and j. Hat instead of an arrow tells me that those are unit vectors. And unit vector magnitude of I is the same as magnitude of j and is exactly 1. Now you will ask, 1 what? Whatever quantity that unit vector represents. So now take a look what happens. Again, let's sketch my vector A. And here we go. A of x vector. According to what I just said, and according to this definition of multiplying vector by a number, I can always write that A of x vector is nothing but A of x magnitude times unit vector I. This is so-called unit vector representation of vector A of x. Exactly same. A of y is nothing but magnitude A of y times j. And overall, vector A can be represented as A of xi plus A of yj, or the last expression is so-called vector A in unit vector representation or unit vector notations. Scalars A of x and A of y are called scalar components of a vector A. Now, if this is theta of A, then using the right angle triangle, we can easily calculate A of x is A cosine theta and A of y is A sine theta. Okay, now adding two vectors in analytical form or using trig becomes really easy. So let's say in xy plane I have two vectors. Vector A given magnitude 5 meters at 60 degrees with respect to positive x-axis counterclockwise, and vector B given magnitude 3 meters and at 145 degrees with respect to positive x-axis. So here we go, my vector A and my vector B. Word of advice, don't try to save on paper. Make your diagram big and easy to see. So here we go. I will move my vector B to arrange A and B head to tail. And the resultant is vector C. Which connects the beginning of A and the end of B. So here is my vector C. Now, I will find what is vector C if vector C is A plus B. So the procedure is very simple. To add two vectors or more than two vectors, you need first calculate x and y components of each vector. So here we go. Here is my theta of A, and theta of A is 60 degrees. Therefore, AX is A cosine theta of A and is 5 meters times cosine of 60 degrees is 2.5 meters. A of y is A sine theta of A and is 4.3 meters. Vector B, its x component is B cosine of theta of B, and here is theta of B. Is negative 2.46 meters, and B of y is B sine of theta of B, and I will show you. So vector B has magnitude of 3 meters times sine of 145 degrees, and this is 1.72 meters. Second step in the process is to calculate C of x as A of x plus B of x, which is 2.5 negative 2.46, 0.04 meters. And C of y is A of y plus B of y is 4.3 plus 1.72, 6.02 meters. The third step is to calculate magnitude of vector C. So C has magnitude square root of C of x squared plus C of y squared is, again, depending on the calculator. When you do this operation, you probably better to use parentheses. So square root of parentheses 0.04 squared plus 6.02 squared, and the result is still 6.02. And my vector C makes an angle theta of C with positive x-axis right there. Which is calculated as inverse tangent of C of y over C of x, and that is inverse tangent of 6.02 divided by 0.04, and it gives me 89.6 degrees. Which is corresponding to my sketch. Okay. Now, where did this inverse tangent of c of y and c of x and this equation came from? So guys, if I will take a look at this right angle triangle, this is my c of x, this is my c of y. As you can see, c is a hypotenuse. Therefore, according to Pythagorean theorem, c is square root of c of x squared plus c of y squared. And if I will take a look at this angle, this is my opposite, which is c of y, and adjacent c of x. Tangent of theta c is nothing but the ratio of opposite to adjacent. Therefore, theta c is inverse tangent, or sometimes called arctangent, of c of y over c of x. The problem is, your calculator is not as smart as we want it to be. It's really easy when the angle is, or the vector is, in the first quadrant. But it becomes a little bit more complicated if the angle is in the second, third, or fourth quadrant of the unit circle. Okay, just to remind you. So let's say I have a circle with radius of 1 meter. So let's say I have a vector in the first quadrant, vector A. As you can see, both components of this vector are positive numbers. Vector B has negative x but positive y component. Vector C has both components negative. And finally, vector D has positive x but negative y components. Those quadrants which are made by x and y axis are numbered first quadrant, second quadrant, third, and fourth. So, depending on where your vector is, and it's really easy to determine, you just look at the components. Your calculator will give you either positive or negative number, and I will summarize how to deal with that in this little table. So we have quadrant number, x component, y component, and result. So, quadrant number 1. Both x and y components of my vector are positive numbers. And you trust your calculator. Second quadrant. X component is negative, y component is positive. And you have to add 180 degrees to whatever your calculator shows you. Third quadrant, both x and y are negative numbers. You still add 180 degrees to whatever your calculator gives you. And fourth quadrant, positive x, negative y. And you do calculator plus 360 degrees. So, example. Vector C is given as in unit vector component form as negative 5i's minus 7j's. So c of x is negative 5 and c of y is negative 7. So looking at those, both components are negative. I know that my vector is in the third quadrant, and when I'm trying to calculate theta of c is inverse tangent of c of y c of y is negative 7 divided by c of x negative 5, and my calculator spits me 54.46 degrees. So to find, remember one more time, my vector is in the third quadrant. So I simply need to add 180 degrees. So 234, and third quadrant is from 180 to 270. Now my result is correct. All right, a short summary. Any vector A having magnitude of A and making an angle theta of A with respect to positive x-axis can be represented as A is A of x plus A of y in vector component notations. Vector A can be represented as A of x I plus A of y j in unit vector form. Vector A has magnitude a of x squared plus a of y squared, and vector a makes an angle theta of a, which is inverse tangent of a of y over a of x. True for any vector in xy plane. In the next lecture, I will show you two more operations on vectors, which are scalar or dot product of two vectors and vector or cross product of two